Good morning, everybody. Today I'm going to talk about cloud computing and quantum computing. First of all, let me thank you, the organizers, Stephanie and Davida, for giving this opportunity, and thank you all for coming. So, I work at the ITRI, Institute for Digital Research and Education. We have a research unit in that called Virtual Computing Laboratory. What we do in that is that we look at the upcoming technologies and investigate and see whether we can apply that into high-performance computing. So that's what we do in this. Apparently, I closed the slide. So while Ron is doing, I'll talk about more about the cloud computing and quantum computing. So cloud computing is where there are some definitions you can do cloud computing and virtual computing. Virtual computing is where you have virtualized operating system and running on.
Yeah. So it doesn't pause. So I use the mouse. I won't plug it in.
Okay. I'll use this arrow. Okay, so first of all, let us look at the Gartner hype cycle, because those of us who are looking at the upcoming research, we pay attention to what the Gartner group is doing. And in this today's talk, we have two items. One is the quantum computing right here, and the cloud computing right here. So Gartner looks at technologies coming out of laboratories, and the technology innovation triggers here. And after a while, there will be a lot of hype, everybody talks. So it reaches the peak of inflated expectations. Then the cloud computing here, it went through all these stages, and the quantum computing is now starting it. So there will be all the hype, then there will be some illusions, people find a lot of problems, and there will be something, what is realistic, what is hype. And then it goes through a trough of disillusionment, then it goes to a trough of enlightenment and flight of productivity, then it goes out of it. So we tend to catch the upcoming technologies somewhere here and investigate and see whether we can use that in our high-performance computing environment. So we followed the cloud computing when it was here, and we're still following it. So this is what I was talking, the attributes of cloud, National Institute of Standards and Technology, have given us some definition what we can call cloud and what we cannot call cloud. So here, in order for a service to be called cloud, it should be on demand, meaning that there should not be any human being in between when you ask for the cloud service. You should be able to go to a web page or log in through the network and sign up for the service, showing up your credit card or some kind of identification saying who you are, and use that service. So network access is a must if you have to do that, because you should be able to do it from anywhere in the world, just through the network. And the resource pooling. This service should be not be just for one person, should be for multiple customers. That's what resource pooling means. Elasticity, you all know the Amazon cloud. According to the demand, the resource should shrink or expand. And there should be some way to meter the service and bill it, so that the service providers can tell you how much resource you use and you bill it. These are the examples of it. Today we will go a little bit about OpenStack infrastructure as a service, because that's what we use in our research. So infrastructure as a service, the way everybody deploys that, as a service provider, we provide only the hardware and a hypervisor. In our environment, we use KVM. You can use Zen or anything else. And the users come with the rest of the thing. It is the user's guest operating system. Normally, this will be some Linux operating system running on it, at least in our environment. And then guest operating system can be Linux, Windows, or anything. Then you have the GCC or the binaries, applications, MATLAB, or anything, and your data. So this is, we don't control this one. The users control this. We just provide this service. And according to the cloud definition, we have provided other means so that users can use. And another way to do any work is through Docker. So Docker is becoming very popular at least in the last couple of years. Docker is kind of like the IaaS, but here instead of that hypervisor, you have a Docker engine. The difference between the Docker and the OpenStack kind of cloud computing is that OpenStack users can have their own kernel, but here the Docker engine shares the kernel is shared, all the containers share the kernel, and it's running on user space. So advantage of using Docker is that you already have Docker. If you have a Linux operating system, it comes with Docker. You just have to install it, and you can start using it in maybe 5 minutes. We give detailed talks of all this Docker cloud in our third floor, in most Tuesdays. So if you want to know the details of all these technologies, you can join us in one of those talks. So how are we using OpenStack in research? We actually use OpenStack in smart manufacturing. This is a DOE project, one of the PAs, Jim Davis at OIT. So we have the OpenStack resource deployed, and this project is to optimize the temperature on a industrial scale furnace which does the steam methane reform. Steam and methane combined to produce hydrogen gas, which is used in fuel cells. And this furnace is very large. It's the 4-story site with thousands of tubes, and the people who are running it, they want to optimize the temperature in all the tubes, and it is impossible to measure the temperature at various end of the furnace when it is when we have thousands of tubes. But we have a mathematical model, and that model runs on our OpenStack resource. So first, it takes there are infrared cameras, the furnace at various ends. It takes the temperature profile, and it is from the infrared cameras, and it runs through the map. That's the smart way of doing the industrial scale operation. So this actually works. The resource where we ran all these jobs. We have around 256 cores of compute power and memory, network switches, and triplicated SIP storage where we did all this work. So when we do the cloud computing, what exactly is happening? So in the beginning, you have your cloud files. They are just like Linux files. It is sitting somewhere in an image store, and you have the compute resource, and this is some kind of scratch space because some jobs need to write a lot of intermediate files. So at the beginning, it is just sitting idle. So when you issue the Nova boot command, Nova is the OpenStack compute software package, it is going and fetching for you. It goes to the image store and take that image over to the compute node, and if you need scratch space, it will load. So this is here, this instance is actually a copy of this thing. So you can have multiple copies of this on several compute nodes or on the same compute node, and once you shut down this instance, everything you did is lost. So this is all ephemeral because there is no, once it is copied, there is no relationship between this one and this one. It is just a copy of it, and if you don't save your changes, you will lose everything. It is ephemeral. And if you need to save something, you need to take a snapshot. That's a simple picture of what is happening in cloud computing. So this is the OpenStack architecture. So the OpenStack has three main pillars, we can say. That is, one is the compute, that is the KVM hypervisor, the network, that's Neutron, modular layer 2 plugin. We will talk detail about Neutron today. And the storage, we can use the SAP or storage, that's a block storage, and you can use script, object storage, and also as users, you don't have to remember all the commands. With OpenStack provide a web interface, the dashboard, so you can just go log into the web. You can do all the, you will get a terminal where you can even run X applications. So OpenStack is a complete package to do to deploy the cloud computing as a service for users or service providers, for anybody. It has everything you need to run a complete cloud service. So this is the OpenStack Neutron network deployment using the Neutron network architecture. So at the minimum, if you want to deploy the service, you need a control node, and it will have one interface. And you need a network node. This is where all the IP tables, the DNS mask thread, everything, the tunneling, the whole thing is happening because this uses the software-defined networking, and then compute nodes. So you will at least you will have two switches. One is to manage the network. That through that network we install all the software like Nova, Neutron, all those packages. You pretty much you will do a yum install or apt get install if it's Ubuntu or CentOS. And the tunnel, this is the tunnel. We in our work we use the GRE, generalized router encapsulation technique. So tunnel network goes through several bridges, and then once you deploy your VM, if you run a web service, you need people to access it. So you need to provide a way to go to the external Ethernet. So it goes from the traffic goes from here to through the network node to the outside world. So you can configure it in such a way that you have both-way traffic or one-way traffic, depending on how secure you want it. And this is a way of with Neutron. From the experience we have, we feel very secure about. So this can even be used for any HIPAA kind of research where you want to isolate all the network and you don't want anybody else to look at it. So this is the best we can offer right now in free open source technology wise if you want to do that kind of research. And in this slide, we show our deployment based on the architecture diagram I just showed you. We have the public network here, and we have the network node, control node, and the block storage node. It can be iSCSI or anything used for scratch. And we also have a NATed node because none of our control node, everything is on public net. So we put everything in a private subnet, so we don't need anybody to hack into our system or something. So we protect all the nodes. It doesn't need nodes. We don't. If we don't need to expose into public, we will never expose it. We put it in under NAT, and only the admins go through that node. And for the users, we provide a login node. And these are the compute nodes, which have the management network and connect network. So even the cables are color-coded. So if you want to deploy it, you can just take this picture and get those nodes and connect those Ethernet cable. It will be ready to go maybe in 2 or 3 days. That's all it takes to deploy OpenStack. And these are the packages that you need for deploying OpenStack. Here we have the heat and the compute part is the Nova, Glance is the image storage, Celometer is for billing, Keystone is identity service for OpenStack as a concept of projects and users. So if a complete lab in a department can go to a project and they can have multiple users. So we control everything to the Keystone identity service, and the Horizon is the dashboard, Cinder is the block storage. So all these things make OpenStack possible. And the neutron networking, here is our neutron networking work. So the compute nodes, you have the instances and security groups, and there is an integration bridge, and there is a tunnel bridge here. So when an instance is deployed, the traffic goes through here, through this tunnel interface, DRA tunneling, and the network node picks it up, and it has its own tunnel here, DHCP server, everything, and then it's a tenant router here, and it goes like that to the external bit. So this is the way the software-defined networking in OpenStack works. And why is this possible? It is possible because the latest Linux kernels now support the network namespaces. Network namespaces are like, you have the global network spaces, and you can have isolated network spaces for each tenant. So each user, every user can have their own network spaces, and they have their own loopback, ETH0, ETH1. So since they are isolated, they can even have the same address. And when they are talking to the global site, they are going to the bridge interface. So that's why it can support many networks in the same machine, just by virtue of the namespaces. And if you are on the network node, you can use all these commands to go and ping or debug or anything. So this makes people, if you want to do any high security work, because if you don't want anybody to know what network, as a user you can come, you can create your own network and you can destroy it, and nobody other than the admin will know that you created that network. So this, so that's why people in NSA and use OpenStack for their work. So this is how, if you want to look at the pictorially, this is a different clients network. So if you go to the Horizon dashboard, you can see various networks pictorially. So when a VM is booting, these are the sequences that are happening. The Nova boot first calls the compute driver, and the compute driver calls the Neutron API to create a port ID. Then the Neutron server creates that port ID, port, and allocates an IP address to it from the subnet that user already created, and it calls the Neutron DHCP agent, that's the DNS mask with port ID. And Neutron DHCP agent configures the port ID with IP MAC address. So it gives a fake MAC address for that gateway and the router. The compute driver then gets the network information, creates the port on via that bridge interface software, which software switch, and boots the VM with the tag device and attaches the switch port. And then the Neutron agent gets that port, settles the port, and network flow so that VM can get the address. So when a system is booted, it goes through several processes so that once the VM comes up, you can have a network access. If you don't have a network access to VM, you can't use it. So it goes through all these steps so that users can log into that VM and do their work. So that's what is happening in this thing. So OpenStack does not reinvent anything which is already there. Everything in the circle here, the OpenStack makes. But in the Linux, standard Linux, Memcache, Apache, NoVNC, everything comes with. So OpenStack just uses that KVM. They don't reinvent. They just use that. So OpenStack coexists with the Linux, and whatever improvement comes in Linux, OpenStack uses. So that is the advantage of OpenStack, and it is completely free Apache 2 license. Anybody can use it for business or any other activities, and you don't need to contribute back, but if you contribute back, it is very good. So now I'm switching gears a little bit and talking about the quantum computing. The cloud computing part is over, so completely switching into another computing, which is becoming very interesting now, because even in the last 2014 supercomputing, the D-Wave, they actually showed the qubit, So it is becoming a reality. So let's look at what is the difference between the traditional classical computing and the quantum computing. Traditionally, we are used to digits, zeros and ones, right? But in the quantum world, it is called qubits because the corresponding to zero is the spin up state for the electron and the one is a spin down at the same time. The difference between the classical and the quantum state is that in classically, you can either have 0 or 1. You can't have both. But in the by a phenomenon that is called superposition, the quantum computers can be at 0 and 1 state at the same time. So this is what is making the quantum computing possible. And also there is another phenomenon called entanglement. The entanglement is that suppose if I have a quantum box here sitting on this, and if that whatever spin in that box is 0, there will be an analogous quantum box in the Andromeda galaxy or at infinite distance possibly. It will have the same spin. So two distant, apparently unrelated things seems to be related somehow through entanglement. So they can escape from one another. So these two principles are used in computing, doing quantum computation. The famous analogy is that Schrodinger thought experiment, because the experimenters were wondering about the superposition. So he gave them a problem to think about it. The problem is that a cat is put in a box, and in that box contains a radioactive element. Radioactive phenomenon is a probability phenomenon. You never know when an atom is, when a nucleus is going to decay. And there is also a Geiger counter, and there's a flask of poison, a cyanide poison in it, and the cat is in it. So if the radioactive element decays, and then the flask will break, and the cat will drink the poison, and the cat will die. So that's the thing. But until you open the box, you don't know whether the cat is alive or dead. So Schrodinger asked people to worry about is that. So that is exactly what superposition. That cat can be both alive and dead at the same time. So and also the particles are in perfect unison. Even when separated by galaxies, that's entanglement. So these two principles make the quantum computing possible. And there is also a phenomenon called decoherence, that if you look at a quantum computer while it is doing, you're basically destroying it. So you don't know what is happening while the computation is done. You should wait till the computation is done at the very end to find the result. And since you want to be free from decoherence, you have to do everything at near absolute zero temperature so that you don't have any interference from vibration or external. If there is an interference, you have to redo the calculation again. And at least in the case of DY computers, they use the principle of quantum annealing. That's when everything goes in the lowest energy state. And tunneling is a phenomenon that is existing only in quantum world. In the classical world, the thermal energy is used to go over a barrier, but in quantum world, the electron can go from one place to another, even when it is separated by a huge barrier. So that phenomenon is called tunneling. And the probability amplitude, those are the things which are used in coming at the final answer. So problem gets solved when all the qubits find the lowest energy state. That's what's happening in annealing. So this is useful for problems where you have thousands of states and you want to do the calculation at the same time, because protein folding can take thousands of steps. In a classical way, you have to do each one each one after other, but in the quantum computing, you can do all steps at the same time. So for the time for computing one step, you can do all possible arrangements. And it is also used in factoring. So it is difficult to know the factors when you only know this value of n. So if you want to break the code like RSA, which we use for HTTPS, OpenSSL and all, you can do it in a few minutes in the quantum computer. And that is what is worrying the people like Google, Amazon, because once this people start getting the quantum computer, they will be breaking our current RSA thing. But quantum computing is little, it will take a little few more years. So Google is getting ready when it comes so that they can use alternative methods for encrypting. So qubits, if you have 3 qubits, you have 8 states. This is the classical thing works. And for 4, you have 16 states. So here is analogous to this thing is the 1 state, 0 state, and here it's corresponding to 5. But because of superposition, qubits can be at 4 and 5 states at the same time. So that is the difference between the digits and qubits. And here is the comparison of inherent parallelism in quantum computing. In the beginning, I said in quantum computing, all possible states are done at the same time. So that's why even though you have thousands of steps, you can it takes only the time for the one step. In classically, you have to wait in the queue for each step to go through one after other. But in the quantum world, all states are done at the same time. So for the time for the one process, you can do all the steps. So that is so application where you can take up inherent parallelism. You can use quantum computer, but in classical way, if you want to just read email, you still use the classical computer. And this is somebody did a simulation for the time taken to do the factorization. So if you have 520 bits, classical computers will take this many steps, which is it's maybe sometimes 20 or 30 years, but in quantum computers, you can finish everything in close to 1,000 steps. So that's what is making quantum computing very attractive in certain areas. And this is a paper that D-Wave people published. It shows the tunneling. I was talking the thermal tunneling where you need thermal energy to go through, but in the quantum world, the electron can just pass through the barrier. There is a finite probability you can actually do the Schrodinger equation calculation and find out that probability for that electron to exist. So here is the way the D-Wave computer works. There are several ways you can create quantum computers. Actually, there are 5 ways. But the D-Wave chose to use this method where you have the by playing with the magnetic flux, here you can make the electron move clockwise or anti-clockwise. This is niobium metal at superconducting around 0.3 millikelvin or something. So it's the spin is up if it is going in this direction, the anti-clockwise direction. If it is going the other way, clockwise direction, the spin is down. So by changing the direction of the electron, the current flowing at supercomputing, there is no resistance. When the niobium becomes is going at zero resistance because it is becoming a superconductor at that time. So by controlling this, the magnetic field here, the D-Wave can measure, make the spin up or spin down, and this is the corresponding energy states. And through that, the qubits, they make, this is a picture of 8 qubits, and these are the junctions. So by controlling the magnetic field, they can reset, before the calculation, they have to reset the value to some desired state and then let it annihilate. That's how they do the calculation. And this is the one they displayed at the supercomputing. This is the 512 qubit, and so this is what is currently used in the machine the Lockheed Martin has with the USC, and another one is the Google. And analogous to the Moore's law, there is something called Rose's law, where the number of qubits will increase according to this scale. So they started here. So now the current one, they have 512 qubits. So each of these machines costs $10 million. So when they are ready to accept university researchers like us, we will try to get an account and start doing quantum computing. So that's all I have for today's talk. We can have any discussion on the quantum spooking effect or anything now. And also we plan to continue the quantum computing in our Tuesday meetings. So there we will discuss the quantum gates and the different algorithms like Peter Shor's algorithm to do quantum computing. So if you guys are interested, just send me an email. I will invite you when we have the next talk.
So the quantum computing is like target very difficult problems. Is there any futurists thinking or talking about ideas that might trickle down to the consumer eventually?
I mean, breaking the Yeah, the question is whether anything that any consumer level problems that we eventually, breaking the RSA algorithm is consumer level, right? We order everything through the web thinking that our credit card number, nobody gets it, right? But once the quantum computer comes in, they can crack that algorithm in 3 minutes, right? So that's scary. Yeah. So, but there is another, by that time they will come with the quantum encrypting. By quantum encrypting, if somebody looks at it, the other person already know that somebody looked at it. In the traditional world, if somebody hacked it, we don't even know. We continue to use the credit card, right? But in the quantum world, if somebody looks at it while it is doing computation, it completely destroys it. So, and that is why the quantum computer has a lot of failures, right? When you do the calculation, if there is an external interference, because you interfered it, right? So the whole computation stops, you have to start again. And so that's why D5 is trying to reduce the temperature even lower so that external interference is minimal. Thank you.